In today's video I want to look at limits, and this is what will take you into Calculus 1 and kind of where you start in that course. So I want to look at what exactly is a limit. So I've taken this function f of x is equal to x squared, so I've drawn the standard y is equal to x squared graph. And I'm going to look at this point where x is equal to 3. Okay, at x is equal to 3, we know that the y value is 9. But I want to look at what's the limit of f of x as x approaches 3. Okay, that's what this means. I'm looking at what's the limit of f of x as x approaches 3. Okay, what does this mean? Well, I want to look at, as we approach that value x is equal to 3, what does my value of f approach? What does my function value look like as I get closer and closer and closer to x is equal to 3? Okay. Now I need to consider this from both the left and the right side. So what happens as we approach x is equal to 3 from the left, and what happens as we approach x is equal to 3 from the right? Okay. So as we can see, as we approach from the left, we get larger and larger and larger values of f until we get to that value where x is equal to 3, which gives us a function value of 9. So we get closer and closer and closer to that function value of 9 from below as we approach x is equal to 3. As we approach x is equal to 3 from above, we get closer and closer and closer to this value of 9, this time coming from larger values. But both times, whether we approach from the left or we approach from the right, we still end up approaching that same function value of 9. Okay? Because of this, we say that 9 is the limit of f of x as x approaches 3. Now, you may be saying to yourself, what's the difference between the limit of f at a value and the value of f at that value? Okay, so we've said here that the limit of f of x as x approaches 3 is 9. So we've said whether we approach from the left or the right, as x gets closer and closer and closer to 3, our function value at that value of x gets closer and closer and closer to 9. So the limit of f of x as x approaches 3 from both the left and the right is going to be 9. Okay. But we also know that f at 3 is 9. So what's the difference? The difference is that this does not have to be the case that f of 3 equals 9. What would happen if I took the exact same function, but this time I decided to put a discontinuity at x is equal to 3, and instead, this time, at x is equal to 3, I have that my function value was 15. So now my new f of x is going to be x squared when x doesn't equal 3, and 15 when x equals 3. This is my new function that I'm going to take. And I'm going to now look at what's the limit of this function as x approaches 3. So as I approach 3 from the left, so as I plug in larger and larger and larger values of x, my function value gets closer and closer and closer to 9. Okay? It doesn't approach 15. 15 is this one discontinuity that happens at a point. But still, for my regular function, as x gets closer and closer and closer to 3, my function value still approaches 9. The same happens when I approach x is equal to 3 from the right. So as I approach it from above, as I get closer and closer and closer to 3, My function value, again, gets closer and closer and closer to 9, this time from above, but it still approaches 9. So even with my new function, my limit as x approaches 3 for f of x is still 9. But f at 3 doesn't equal 9. F at 3 equals 15. So this is one of these cases where we can see that the limit doesn't equal the actual function value at that point. That is the difference. Okay. So it doesn't depend on the actual value of the function at that limit. It just describes how this function behaves as you get closer and closer and closer to that limit value. Okay, so it's just a description of how that function behaves as you get closer to that x value. It is not necessarily the function value at that point. Now, if that is the case, and you will do this more in calculus, if that is the case, then we say that that function is continuous at that point. So for our original f of x, where we just took f of x is equal to x squared, that function is continuous at x is equal to 3. But now, with our new function, we have this discontinuity, where we have this point that is removed, and we have that at x is equal to 3, f of x equals 15. But that isn't the case for all of our other function values. We have this discontinuity, and therefore our graph is no longer continuous. So for that reason, we see that the limit does not equal the function value at the point that you are approaching. Okay, so that is the difference between limits and function values. The function value is just where you evaluate at that point. A limit looks at how that function behaves as you get close to that value. I want to look at some examples of evaluating some limits at particular points and looking at what some of these problems may look like. And I will do more of these in our next limits video as well, so that you can see different types of examples that you may come across. The first example that I want to look at is the limit as x approaches 2 of x squared plus 4x minus 12 over x squared minus 2x. Okay. The reason that I want to go through these examples is kind of going back to what we just talked about with evaluating functions at that particular x value. If I evaluate this function at x is equal to 2, I would get 4 plus 8 minus 12, so I would get 0 on the numerator, and then I would get 4 minus 4 on the denominator, which is still 0, so I end up with 0 over 0. So I know here that I've got like a discontinuity, I've got an asymptote, something is happening here to where I can't just plug in that value into my function and expect that to be the answer as my limit. So what do you do in this case? You try to simplify. Okay. So if I take this function here, x squared plus 4x minus 12 over x squared minus 2x. Okay. What I would do in this case is try to factor. Okay. So if I look at my numerator and I factor my numerator, I should get x minus 2 and x plus 6. And then on my denominator, I see that I've got an x that is common to both terms, and then an x minus 2. I have an x minus 2 on top and bottom. So what I'm going to do is I'm going to cancel those out to leave me with x plus 6 over x. So now what I'm going to do is say that provided that x doesn't equal 2, I know that x squared plus 4x minus 12 over x squared minus 2x equals x plus 6 over x. That is true as long as x doesn't equal 2, because when x equals 2, I will have cancelled out a 0 here, which of course we can't do. So as long as I know that x doesn't equal 2, I can get very, very close to 2, but as long as x doesn't actually equal 2, I know that these two can be the same. I know that I can say that these two expressions are equal as long as I don't have x equals 2, because then I end up with actually cancelling out a term that has a 0 in it from when you plug in that x is equal to 2 value. Okay. So now I can evaluate this limit just by plugging in that value into my new function. So the limit as x approaches 2 of x squared plus 4x minus 12 over x squared minus 2x is equal to the limit as x approaches 2 of x plus 6 over x. Again, we can get very, very close to 2, so I want to see what's the behaviour of this function as I approach 2. I don't care whether x actually equals 2 or not. I'm just looking at what happens as it approaches it. So the limits of these two functions are the same. Then I can just plug in x is equal to 2 at this point. So I would get 8 over 2, and that equals 4. Okay. So whenever you get one of these problems, when you originally plug in that value of x and you find out that you get 0 over 0, knowing that this won't work, see if you can simplify in some way such that as long as your x value doesn't actually equal the value that you are approaching, you can then set these two limits of functions equal to one another, because you know that you're just worried about what happens as x approaches that value, not actually what happens when x equals that value. So then you can just go ahead and simplify, and at that point you should be able to plug it in and figure out what the limit is. Another example I want to look at will kind of take you into what you will be doing with calculus. So we're going to look at what's the limit as h approaches 0 of 2 multiplied by negative 3 plus h squared minus 18 all over h. Okay. Like I said, this will look very familiar to some of the problems that you will be looking at when you get into Calculus 1. You will be dealing with a lot of limits as h approaches 0, and it goes back to that difference quotient that we looked at the very start of this course. So in Calculus you're going to be combining that idea with this idea of limits as h approaches 0 for those difference quotients. So keep that in mind when you start Calculus 1. But right now I'm going to look at the limit as h approaches 0 of this function. Okay. Again, if I plug in h is equal to 0, I'm going to get 2 multiplied by 9, which is 18 minus 18, so I end up with 0 on the numerator and 0 on the denominator. So I know that I can't just plug in h is equal to 0. So let's see if I can simplify this function in some way. So I'm looking at the limit as h approaches 0. I'm going to multiply this out and then see what happens. So negative 3 plus h squared would be 9 minus 6h plus h squared minus 18 over h, which is the limit as h approaches 0. If I multiply this out, I'm going to get 18 minus 12h plus 2h squared minus 18 over h. The 18 and the negative 18 cancel out, which gives me the limit as h approaches 0 of negative 12h plus 2h squared over h. You should be able to see here that we can cancel out the h's as they occur in both the numerator and the denominator. We can cancel them out because we are not worried about when h actually equals 0. We're worried about what happens as h approaches 0. Okay, so if I factor out the h on the top, I should put the limit in front of that. So I've got the limit as h approaches 0 of h multiplied by negative 12 plus 2h over h. And like I said, we can cancel out the h's because we're not going to set h equal to 0 at this point. We are just worried for this function what happens as h approaches 0. So we can cancel out the h's because it doesn't matter about dividing by 0, etc., etc., because we're only looking at what happens as h gets very, very close to 0. Okay? And when you do that, at that point, we can plug in h is equal to 0, and we see that we get an actual value where dividing by 0, etc., doesn't matter. We just have a linear function in there. So we end up with the limit as h approaches 0, negative 12 plus 2h, and that gives me negative 12. Okay? So whenever you get one of these types of problems, just see what you can do to simplify it. You may have to put that restriction in there like we did with our first example. We said as long as x doesn't equal 2, we're good to go, and that's fine because we're looking at the limit as x approached 2. Okay, so it didn't matter about x actually equaling 2, we're worried about what happens to the function as we approach 2. Same thing here. We could cancel out the h's because it didn't matter about h being actually 0. We're looking about what happens as h approaches 0. What does the function value approach? Okay. So see what you can do to simplify these types of functions whenever you get a limit like this. But the moral of the story here for this video is, going back to what we had with our graph here, it doesn't matter what the function value is at that point. The idea of limits is what happens as x approaches a value, what does the actual function value approach from the left and the right? As long as they are the same, as long as from both the left and the right it approaches the same value, you have a limit. If it approaches different values from the left and the right, that's when you have a problem and the limit doesn't exist. But as long as it approaches the same value from the left and the right, even if you have a discontinuity at that point, as you get closer and closer and closer to that x value, you should approach that same function value from both the left and the right. Therefore, the limit exists, and therefore you can go ahead and actually evaluate that. But the function value does not necessarily equal what the limit is at that particular x value. So we cannot definitely say that the limit as x approaches a value of f of x equals f at that x value. That's not necessarily true. We're just trying to describe the behavior of the function as you get closer and closer to that x value.